In Ubuntu, it's a community standard. It's cross-platform. It eats other languages, like you can load PHP into .NET, you can cross Java into .NET, and basically it's starting to consume more and more languages as time goes on, and someday, hopefully all. It offers future compatibility, so whatever your platform today is that you're targeting, you can develop and deploy today, and hopefully your source code might run on tomorrow's architecture platforms, 128-bit processors. And it's platform independent, which also offers us the ability to write malware and cracks that, as with .NET, are cross-platform. So this talk is focused at hackers and attackers. Whether you're here to learn and enjoy and just meld other programs, or you want to attack and do vicious things to other programs, that's what this is about. Whether you want to cause damage to someone else or defend yourself against them, you want to bend applications or the system as a whole, you need the system to bend to accommodate you, or you happen to be deaf and you need slight modifications, or like this guy, you're French and you need just a different way of interacting with your programs, and then once that tiny change is made, it's entirely good. Or maybe you just need a one-off solution. And that's what we as technologists can do. We can bend other applications to be different than they were meant to be. So what's an app? It has our intellectual property, it has the objects and data that we consider to be source code, it has the locks inside of it, and the inherent power that that application controls. And that's what we're attacking. We're going after the application itself. We're able to infiltrate and bend it to whatever means we happen to want to accomplish. So this isn't assembly level, specifically not IDA Pro kind of thing. Because when you're going at an old application that's assembly code, it gives you the power to drive that application. It gives you the power to bend that application. We all know IDA Pro. This is a classic approach, and it was very solid for back in the day. And IDA Pro facilitated us doing what we needed. It gave us the ability to edit and modify small applications. And they looked like this. Literally, their object structure and their source code was quite manageable. You could keep it in your head at one moment in time. And back then, fighting that application or attacking it, you needed tools that were comparable to that application. But now today, this is more what an application looks like. It's hundreds of objects in memory for one small frame, and it's gigabytes of RAM. And that's the paradigm shift. When you're talking about 300 objects or 3,000 objects and 40 threads, that IDA Pro attack and paradigm kind of falls apart. And that's where this all comes in. Using .NET and the IL framework, which is pretty much assembly code up interpreted level. This is IL, the intermediate language of .NET. This is what .NET truly is. And this is where we attack. This is where we get that same ability to bend and control applications that we had in IDA Pro, and we just use this same power that we've always had to attack our applications in the same fundamental, undeniable way. Let me walk you quickly through a quick example of decompiling 13 lines of C# code. When you compile these 13 lines of C# code and then decompile them, they turn into 15 lines of C# code, 34 lines of IL, and 77 lines of assembly code. And that is the factor of how much time you're going to need to spend to read them. So when I say 15 lines of C#, it comes out fairly readable. You can quickly peruse it, see what it did, figure out if it's malicious, vulnerable. The 34 lines of IL, a little more to read, you have to know IL, and it gets a little more ambiguous. And then once you get to assembly code, even if you know assembly code well, it just gets bloated, and now you have to spend a lot of time processing what it does and does not do at any given moment. And so that's why IDA Pro just isn't the tool for this, because you don't want to be doing 77 lines of processing for 13 lines of input. Because if you do, your projects will just lead you nowhere and it'll just be painful. And so that's where I come in, attacking on memory and on disk. That's my thing. We're going to attack application on disk. When we attack this application, I'm going to be using a tool that I wrote called Grey Wolf. It allows us to edit an application and give it fundamentally different behavior. So let's look at attacking on disk. This is the old paradigm of attacking, and now we're shifting to a more visceral, strong approach. That's what I'm hoping. So let's look at attacking Microsoft Media Center. What does it take? What is it built out of? And yeah. So let me walk you through that demo. Okay. So here's Media Center. The core fundamental ability of reaching into another application and modifying it is that it works against ubiquitous targets, regardless of who made them or what security they were made out of. So down here, back programs. So this is Gray Dragon. It injects us into our target, and I drag and target our executable. It finds it's a 64-bit target, and we drop a payload in, and then it runs an executable inside of our target. At this point, we're able to execute source code inside of our target as if we were part of it. We can drag in an arbitrary payload and load it inside. And so now I've introduced an arbitrary executable that shimmed in another one, and we have a couple of buttons. Over here in Media Center, this payload attacks the password sequence. So we can type in any password we want, and it doesn't let us in. Actually, real quick, why don't I rewire that? So that was Media Center. I'm going to rewire it real quick just so you can see it. Okay. Okay. So I figured I'd rewire it so you can see the passwords that I'm typing in. And that's part of what this brings us. We can edit arbitrary things inside of our program as if they were our own. So I can type in a password, and the password is 111. The password isn't 000, right? That's where injecting and attacking comes in. We inject in, same thing I just showed you a second ago, except for now you can see the password. Drop in our payload inside, load it up, and so now we can come in here and say, let's set it to 000. And also we can grab the MD5 hash of our current, but we'll change it, and now the password is 0000. And that's what it takes. You can introduce new functionality into your target and just call core functionality and be like, I want yours to be 444. And so when you think about attacking this, what does it take to get into an application and quickly bend it? In this model, I'm injecting in a payload that I wrote in 15 minutes that overrides a key security feature. And this isn't that Media Center is specifically weak, which it is specifically weak, but you can go against harder targets. And I handle all of the threading, so like when this window closes, all of the payloads that are inside of it close, and I take care of all of that high-level stuff to make it nice and easy. You can just shove in any arbitrary void main you want with these tools. So it's not like Metasploit and you have to come up to speed and write some hardcore thing. It's just, you pack in whatever void main you want. And that's attacking Media Center. Looking at Grey Wolf, just to take a quick aside, you can take these payloads that I'm writing, drag and drop them over here, and this is Grey Wolf, the decompiler. You can open it up and tunnel down into the namespaces. So here's the payload we dropped in. We can open up, go to change password button, and you can pull up my source code. So we can tunnel in there, and this is the source code for that. And that's kind of the thing, that we're a level higher, so getting source code is slightly easier, but it's pretty much the same thing that we did with Soft Ice back in the day, just coming back around in .NET. And like I said, when you're talking about what does it take to read through this, here's the IL for this, and then here's the source code. It's definitely a factor easier. And same thing when you're going at it with assembly code. To understand what this function does is dramatically easier this way. And you can vet my program and see if I put a backdoor in it, which is kind of nice. You can trust but verify and start treating everything as open source and verifiable. So to break it down, if you decompile Media Center and you start looking in, you find it's check pin. It's a function called check pin. It takes a string in. Looking at the flow, you can say, okay, it comes down here, it pulls out the currently existing pin. It checks to see if it's equal to null. It checks to see if the length is greater than 0. And then it has a peculiar branch that if the 0th character is a colon, then it has an arbitrarily different sequence for logging in. Kind of interesting. When you're brute forcing, you might not notice that. And then it does the return validation, or it does the alternative logic of validation against something slightly different. So there's actually 2 login modules inside of this one program. And that's partly what this brings us. When you're doing black box testing, it's kind of hard to get that. But everything's white box when you're willing to go in and pull out source code. And of course, I just go in and put a return true when I want to get past the password. And so as I showed you the password, I could just as easily put a return true and drop that in there. So let's look at it from the other side. Instead of attacking applications that are hardened against us and all of that, let's turn it around into, there's antivirus.exe, and you got a pop-up and it said you have an antivirus, or you have a virus, so download this and we'll take care of it. You can drag and drop it over here, and let's do a quick walkthrough. You can go to find main, and then you can find your main and see where it starts executing. And this is probably malware, but we have no way of proving this. You look through, you see obfuscation, and this is the same thing that anyone defending their program against you will do to try and make their program quite unreadable. So that's where Grey Wolf starts to step it up a notch. You can come in here and do an import, bring the same antivirus in, run it through a deobfuscator, and now our void main has better naming, and now we are starting to get real names back. And what was arbitrarily hard to read before is now starting to get significantly easier. And so when you're thinking about malware and they're starting to do obfuscations, packers, RSA crypto before it pulls it out in memory and then depacks it and executes it, this undoes that. Anything that's done in a programmatic way can be programmatically undone. And so both sides of the coin, whether you're defending applications or attacking applications, this is just one more tool for your tool bag. So let's say you're digging through their source code, right? And you find something like, let's see, okay, sure. Let's say you find maybe a string, and it's like, well, if the string was different, I might be able to send them back bad data or get them to do something arbitrarily malicious to them, right? So over here is a string in IL, and here's a string in code. You can come in here and just be like, I want it to drop all tables. You can just do whatever you arbitrarily want to their program. And that's where I'm going for modifying. I'm not decompiling. And part of the not decompiling paradigm is you can take this back to source code, but you can also just make an arbitrary change, hit save, and then save an executable right out, and then fire it up or push it at them. Or maybe instead of doing that, we want to do something like add a call and put a call in there, and then make a call out to some other function somewhere else. And so that allows us the ability to, let's see, find this call. And so we can put arbitrary calls in there. We can put in other payloads. We can add other libraries. We can just modify it like it was pure source code. And this isn't executable or a DLL that's just deployed on the internet. And we can start taking that full control. That, like back in the day, we all know that like there was hardcore assembly programmers that could just modify an executable, right? And we lost that? No, we didn't lose it. We just forgot about it a little. We kind of put it to the side. Oh, assembly code, it's real hard. And this is assembly code for .NET and Java and all the rest of it. So that's on the other side of the fence. When you're going up against malware, the ability to just rip through an application, quickly modify it, and fire it back or push it back out could come in handy depending on what you're doing. So let's look at specifically injection for just a little bit. An application's running in memory, you come in, you deliver your payload inside of it, and that's your attack. When an executable spins up, it fires DLLs, it uses all sorts of verification. This all goes through the ubiquitous Windows .NET security systems, and it becomes a process. Whatever scanning, whitelisting happened to take place. And then after all that's done, we come and drop in our payloads. And this is the upside of injecting in .NET. You can come in at the last moment in a high-level language, either through Metasploit or having access to that core system. You can come and do that attack. And so let's see what we can do with that. Let's inject one payload into one application. Let's inject that exact same payload into another application, and so on and so forth. And these are applications that are different architectures. One is 32-bit, one is 64-bit. This could just as easily be one on Linux, one on Windows, one on your Xbox. You could take the same payload and push it against multiple targets. So here's a protected packer. It requires a password, and once we give it the password, it unlocks its features. Let's inject in there. So this one payload is attacking a 64-bit application, right? So it uses a 64-bit bootstrap, and now we have our 64-bit bootstrap up. This bootstrap is compiled into MSIL, which is neither 64-bit or 32-bit. That's why it can work anywhere. We can load in hack, drop it in here, and now we're able to add functionality to their application, where we can iterate all strings and just change it. Or we can change the locations and values of any object in memory. And so like this button that I can't click down here, I can just say, oh yeah, you can. I can just edit arbitrarily any value in memory, any object in memory. I can just walk in there and body snatch it, replace it with a man-in-the-middle object, and go to town. Pretty much anything you can think of as a developer, you can now do to arbitrary applications on the fly. Okay, so this payload that we're going to inject in there, right? We can load in as many of these payloads as we want. And I manage all of the threading, all of that GUI stuff, all of that gets managed up here. So this payload looks through the application and it finds the hash that it's validating against, and then it runs a brute force crack. And so it's like, okay, here, I just brute forced it. I used its arbitrary code for checking the hash. I got a validation, and that's it. And then I'll type it into the text box because that's a feature. Okay, so there it is. Let's kick it up a little bit. And again, something that'll take a little bit of time to process. So again, like I said, drag this target in here. It says, okay, I see it. It's 64-bit. Here's its process ID. Inject in there. Drop that in one more time. And it pulls out a different hash because this one has a longer password. We start cracking it again, and it uses the functionality of its target to process the checks. So you're not trying to recode and emulate it, you're actually using its own functions and its own hash code values to check against. So this is why one single payload can work against multiple targets, because you identify what you want to lock onto, it will just process it, brute force ubiquitously until it finds it, and then that's it. And that's a 64-bit application, right? So like I said, we're going to go up against a 32-bit application again, a different application, inject into it with exactly the same payload. So it's a 32-bit application, something entirely different, made by someone that's completely separate from the other one, right? We'll inject in, and this time, let's drop in one extra payload. So like here's a code access payload. It's going to wipe through the entire memory space and then pull out the source code in memory. So as I was doing it on disk before, this walks through and rips that out of memory. Anything that you can do as a programmer, you can do here. You can edit, you can pull out of memory, you can push. Okay, so back to the payload. Drag and drop the same exact payload in there, right? Okay, so we have our payload, we have the hash, and we have our brute force. This is a completely different hashing sequence. The previous one was a simple MD5 hash. This is a SHA-256, then MD5, and then a proprietary. And so it's a chaining. And so as before it was processing tens of thousands a second, this one's processing tens a second. And again, we're using the functionality inherent in them. We're not bringing the functionality with us. So we wait to lock onto a target, and then at that point choose what functionality we want to pull out and use, where we want to pull the hash value out. And that's why it's a ubiquitous brute forcer. Again, it finds the password, types it into the box, and then validates. And so now instead of writing a brute forcer to a target or brute forcing a single technology, you can write an adaptive brute forcer that will work on literally any program that you can identify. Here's a hash, here's some RSA crypto, here's maybe a function called key check, and why don't you lock onto them and just brute force until you can return me true. And so let's look at something a little more real. In the real world, we want to go up against passwords. We want to pull out free software. We want to really destroy applications, right? We want to critically wound some business. And so we can deploy password brute forcers. We can inject our own sequences of communication straight into their stream. We can send things that should never be sent, right? At this point, we can say, okay, you had a SQL object that you SQL cleaned. Well, we have the SQL object, so we can just fire anything we want at you. And now you have to consider that a high schooler can now get into your SQL object and just start SQL injecting you in a matter of seconds. Well, that's a bad idea, of course. We don't do that. We wouldn't do that because that's not legal. But we have to consider this is the same tool, this is the same stuff that everyone else has access to. And so keep that in mind. Like, this isn't a benign threat. But also, like I said, this isn't new. So we should have been taking care of this 20 years ago. Every single program that's on the desktop should be immune to SQL injection. But how many developers for the desktop do you think do SQL cleaning, much less any defensive mechanisms? Like, close to 1%. So what does it take? You connect to your target, you do some decompiling, you get in, you find out what technology they have, you infect it, you change the target, you exploit its core vulnerabilities and take advantage of it, and you remold it and win. Here's the weak spots that I think are vulnerable to go after, kind of a top 5. So flipping the check in an application, setting a single value to true, cutting the logic, returning true, and accessing a value. This is because you can come in and say registered equals false, now becomes registered equals true. Or a Boolean check for does A equal B, like on password validation, you can simply say A not equal B. And with that simple change, only invalid passwords will pass. Is registered true? You can just throw that at the top. SQL cleaning, throw it at the top. Yeah, it was SQL cleaned, and now you've negated all of that defensive mechanism with one single command. So let's look at that. Let's look at attacking the login sequence of a real application. So we'll run this. Come into settings, general, security, and put in a password. Okay, so now we have a secured application. Anyone tries to come in, they'll be presented with a password challenge, and if they don't know it, they can't get in the application. Like I showed you before, we could do brute forcing or whatever else. Simply in Gray Wolf, drag and drop it, open it up, and at this point, we can come down to P and U. So this is the password validation. The password validation is simply take our input and compare it in plain text, no crypto around it, just simply do a straight comparison. So at this point we have the plain text of the password and the plain text of the stored password, and that's our comparison check for this program. So let's attack that. This is IL. Okay, so here we get our password. We'll start adding some new IL in here. Okay, so this is our get password, and this is our op equals. So kind of like when we had to learn assembly code, at this point you still kind of have to know IL. Hopefully I'm going to get past that though. But here's the op code. This allows us to put in a new instruction here. We'll call it dupe. And I've tried to make this easy, so down here it tells you the definition of dupe. So it duplicates the object on top of the stack. So now we have our currently stored password, and now we have 2 on the stack. We'll put in another line to a call, put a call out, put it out to system, Windows, forms, library, tunnel down, and we put it to show. And so now we have our password on the top of the stack showing out. This function returns something, a dialog result. We'll put a pop because that's on the top of our stack. And now this is what we have. We have get your password, show it, and compare. That's pretty good. We come down here and we have this op equals. So let's pop this off of the stack. So whatever op equals did, we'll just destroy it. And then we'll put in LDC I4 1. And so, like I said, here's our comparison. We do our comparison, and then we if true. And so now this is our validation sequence. Click save it out. So now let's go in and try and log in again. Okay, so put in a password. Here's our password. And that's it. Those couple instructions have completely not only negated, but given up the stored password. And that's going from a hardened application, and this kind of R&D attack is easily doable under 2 hours. You can go from scratch downloading to a fully deployable attack in under 2 hours, if you're skilled, pretty reliably. If you're unskilled, maybe 8 hours. But if you have general programming knowledge, certainly within 1 day, you should be able to affect some program in a fundamental way. So let's look at this. We have these settings in here, and come into license, type in LayerOne 2012, and unlock the program, because that's a registration key. It's like, no, that's not a registration key. Why would LayerOne 2012 be our registration key, right? Well, let's go and fix that. Come down here into, so this is an obfuscated program, right? They went through and they put in bad names. Coming in here, core, the static constructor. This is where the initial values of the program are set. And here's our target variable. This target variable controls what it's keyed against. So we come in here, put this in here, change this variable. As I showed you before, you can change an arbitrary string. I changed the arbitrary string. And now that arbitrary string is going to work, hopefully. Save it out again. And so now we have a second version. We have the original crack that we deployed, where it gives us access past the password, divulges, gets us in, come in setting, license, LayerOne 2012. Okay, that's kind of embarrassing. Maybe it's AppSec USA 2011. Okay, close enough. And that's what it takes to rekey an application. So you can consider this to be like the signing sequence of an application, or anything else, or when it downloads updates off of the server. Like, this stuff is completely benign. Like, you can't go out and hurt thousands of people with this. But this is the benign version of what you can really do against a protected application. And so those couple of little changes are considered hardcore cracks today. Like, okay, get me past the login sequence and crack the application. And you can do it in about 20 clicks. Like, that's it. It's just a couple of lines of IO. And so it's dropping that bar of what we consider a threat to be someone that has MIT skills, assembly, and they have funding, to some kid in Bangladesh with an extra 2 hours between classes. And this is a new threat model. So let's look at it. You have public and private key signing. You simply change the key. And now you can just push out and own that application. Common validation sequence for keys is you have an unknown value. You put in your name and ID of the machine, and then you happen to know the known value, what is /b, and that's it. And you're able to crack that sequence. Call the server, just hack the call, point it to your own server, or negate that server call, whatever you want. You could be phoning home critical information and then say, yeah, your program's validated. You can do anything at that point. Demo equals true, you can set it to anything you want. And lots of programs will have this in the first 3 calls of the application. Right under void main is set whether it's true or false. And this is a common programming standard, which is fine. And then there's complex math to try and defend the application, which is nice and fun because it takes complex math and thinking to unwind it. It's like a Rubik's Cube that no one wanted you to solve. And way more than 1% of the time, they'll ship you the key generation sequence inside of their program. Right next to the key verification is a key generation sequence. Because they bought an off-the-shelf product, included the DLL, and shipped it. And that's just part of the market. It's trust but verify, but on the desktop side, how many people have really done a security review of their desktop application? Like, you're pen testers, right? How many of you have ever hardened a desktop application? Heard of anyone? Ever had a client say, we have a desktop application we're using on tens of thousands of terminals, and we want it to be secure and it can't attack the server? It's just not in the threat matrix. So that's why I'm here. I'm showing you that if you have a key sequence, instead of trying to beat it, you can simply change it. When you have a server call, you can have it point to any server you want. You can send back any information you want, and then you can complete the sequence. And this is a fairly ubiquitous thing. And we can do replay attacks. So like, here's a sequence. You pass in your name, it turns into a random code string, and then we check to see if the registration code equals. That's nice. And then we can just replay the same sequence. And we can use this against tens of thousands of applications in a matter of minutes. And this is just low-hanging fruit, because for the longest time, this is a completely undefended front. And complex math, you simply chop it up, you attack the weak spots, you put in brute forcers, and then you spend a night undoing it, and by the end, you've cracked their complex math. So, this program, just to talk about it a little bit, like, what do you see inside of an application? So this application encrypts your data. It stores it in a static key. It uses zero vector initialization. It stores your text password in the clear. So if you're doing a security review and this is a product they're either bringing in-house or they're producing, you can start coming back with these definable things. You need to fix this, this, and this, and remediate it. And then build that into the cycle and build a hardened cycle of development. So what stops all this that I'm showing you, right? So what's the security that we have to go up against? What will companies do to try and stop this? They'll try and protect this with obfuscation, just like that antivirus program that I showed you where you just pull off the obfuscation. They'll do code obfuscation, logic obfuscation. They'll make unmanaged calls out to other languages. They'll make shells, packers, crypto, the same exact techniques that your anti-malware people are coming up against. That if you're trying to protect your malware from being reverse engineered, that's the same thing you're doing when you're trying to stop your enterprise application from being reverse engineered. And this tries to shut down decompilation. Because when you have your secure app, you call out to a dongle, you maybe phone home and do Twitter and database calls, you fire off some crypto, and these are the ubiquitous weak points. Because each of these points is a single function call between one library and another. These are choke points that you can quickly get to and just intercept it and say, yeah, your USB dongle is there. I'm going to fire off those server calls. And think about this. If you have an application that has the right to tunnel through your firewall and fire out to the internet and send any arbitrary data it wants, doesn't that seem like a threat? Like, if you have an application inside of your hardened network, like a forensics piece of software, and you have to open a tunnel to allow it to get to the key check server, and this is okay. Why? Because we trust that piece of software, because there's no way that software could have been compromised. And this is just a security vulnerability that we can leverage because people trust their applications. They trust the guards to protect their databases. They trust the programs to protect their databases. And we know we should trust but verify, because when you have this model that it's just secure, and that's the beginning and end of it, you only have to worry about the outside. That's just not the model anymore. And let's look at it. Here's Grey Wolf. Here's this program that we took out earlier. We drag and drop it, and it's like, I don't know. It has no clue about it. And that's because it's protected with a not off-the-shelf packer, all of that. And like I showed you before, we can inject into it and do all of the same stuff. All of that protection falls away. We have, like I showed you before, we can inject into it and pop all the code out of it and look at its code base. And so it's protected in memory against, it's obfuscated in memory, it's unpacked, it's coming from multiple languages, and we can inject it and take all of that away. We can inject it and do other things. So here's another payload. we can add these buttons in there, right? Take another application, like say the brute forcer, inject it in there. And we can take X number of applications and just keep injecting all day long and just keep going, right? And where does this all lead? Where does the ability to inject 30 applications together go? Well, this is where it goes. So like I said, I can manipulate objects in memory, right? These applications, this one, this brute forcer, and this program that it attacks, at this moment are in the same memory space and essentially one application. So I can take something like this crack button, remove it off of here, and I can push it over here. I can take the cancel button, whatever you want. I mean, these are fundamental changes that allow us to do whatever we want to our targets. Actually, I'll just click that button real quick to show you. Right. Okay. I'm a little jet lagged, so. Okay. Okay, so that's the sequence. You drag and drop, drag and drop, drag and drop. You inject into your target. You click this, it iterates all windows and adds these buttons to it. And these buttons do the same thing to its target local values, which can come in handy. Such as, what does this crack button do, right? This means you can right click on this crack button now, and it'll divulge what that crack button fires. And so you can just say, hey, give me that code that's right there, right under your fingertips, here it is. And you can jump straight to that code. And here it is, the pass cracker, its object, its function, and you can pull that right out of the GUI. Like I said, you can pop it off of one application and pop it on the other, and then fire it. And this still functions. This is safe. I'm handling the threading, I'm handling the objects, and it's pretty easy. These payloads are between 25 and 50 lines of code. They're written in a couple of hours max, and you can just churn them out all day long. And so you can make fairly fun cracks. Like you can just make everything run away. You can say, okay, I want everything to dodge this. And it's like, there you go. In 2 lines of code, you can just say, okay, well, you can never click on anything again. And think about it, like, what does this mean? Like, if you come in here and I can add a right click to this, I can come in and say, okay, well, this is a 7.8 font. Well, I have a blind individual and this needs to be a 48 font, right? Now, how long would that take you? If I said this needs to be ADA compliant, this needs to be a 48 font, like, what's your dev time? And if I can say, oh, it's 2 lines of code, and you can do this to any ubiquitous program, it opens up the doors. Like I said, if you want to do a one-off solution for someone and you want to say, okay, it's in French, well, now it's in Italian. It's in Italian, well, now it's in Farsi. You can just go all day long and make ubiquitous converters, ubiquitous brute forcers with a few lines of code. And that's what my tools are bringing you. It's not that this is new, it's just A, free, and targeted at the new platforms. And when I say new platforms, what do I exactly mean, right? So I keep saying, oh, I'm going up against these programs. They're not necessarily vulnerable in some fundamental way. But what does make .NET slightly different? It is a runtime language. So we have things like reflection. We have reflection, we have object-oriented, all of that. And this is LayerOne. So here's Java to .NET. IKVM. IKVM is a general conversion from Java to .NET. It's open and it's free. We'll come in here, take this to the command line because I haven't got around to making a nice interface, but it's written by a pretty cool guy that has some good skill. So that's IKVM. So IKVMC for compile. So IKVM can run at runtime or it can run at compile. We'll target Armitage jar, and it'll go through and produce armitage.exe. That's kind of nice, right? Like, here's armitage.exe. I don't have the Java runtime installed on this machine. We'll boot it up. This is booting the JVM on top of .NET. It's basically handling Java on top of .NET and then Armitage on top of that. And so this is Armitage converted in a couple of seconds over to .NET, right? Well, check this out. This is our injector that works against anything, right? And now it can target Armitage. We can say, okay, inject, and that ubiquitous brute forcer now happens to work. All of our payloads that we're looking at happen to work, so on and so forth. And so we can take something like, like this button thing, drop it on there, load it up, and now we can add buttons. We can edit and manipulate that Java application as though it were a .NET application, which is something new. When I'm saying, okay, if it's in PHP, Python, Java, whatever, you can bring it over to .NET, interface with it, roll it into one application, and deploy it on the .NET framework, on roughly any platform that you want. That's kind of what I'm offering. So when I say this is a .NET executable, you can drag and drop it over here into Grey Wolf and open it up as though it were, and it is. So here we can open up Armitage, Armitage main, and come to the main on Armitage. And so here it is. Here's the main, here's the GUI, and this is Armitage. And so to go from an arbitrary Java application to a .NET application, and then be able to have that same editing capability in one tool set, that's kind of nice. It opens a few doors. And so when you take something like this, we can start injecting other payloads, we can start editing and combining it, and you can now use Armitage as though it was just a bootstrap, or you can write a payload around it, whatever you want. And so that's Armitage in .NET. So back to the obfuscation, it really doesn't make a difference. You can pull it off, you can read it anyways, it just hides the code. So, obfuscation, I just want to talk about it for a real quick second. It's not a terribly important topic, but the downsides of it is it only works against pure privates. So if you have publics, it still allows it through. We can import it, pop it off, but that's okay. I really don't care about obfuscation right now. Okay, so this is a slide from a company that protects your applications. This provides you a platform for intrusion detection, tamper alerts. They'll add this onto your application. And so when we're talking about going up against malware, this is also what they're going to be using. And these tools allow us to edit them and compromise those core protection mechanisms and accomplish the same undeniable attack that we were going for. And I hope that's what you're getting from this. I hope that these tools look fairly easy, that you can go to a hardened program or fairly protected program or an easy program and get that ubiquitous control. And let's look at that for a second. Like, what is it that I'm really looking at? So take Web Inspect, right? It's a fairly large and hardened program. What do you think it's protected with? Obfuscation? All sorts of key validation, calling home to the server? We can drag and drop and find out. We can now know anything about our target that we want. We can just start looking through and say, okay, how did they protect themselves? What standards did they adhere to? And all of that. You can do something like, here's their package scanner. You can come into their package scanner and look for what technology did they use, what standards did they adhere to, and all of that. What code did they use? Here's their package scanner. Yeah, okay. I run a whole bunch of different versions, so I have to boot it up in a different version. So, the package scanner is a pretty large payload, 8.28 megabytes of source code and resources. So we can come in here and we can go, I think it's from, and their package scanner, and do a quick search. It reaches through the entire program looking for froms in this program, and it returns us some. And so at this point, we've reached into their program, typed in a quick search, let's see, and yeah. So, here we are. So we have a database session, we have a create query, we have a from call, and we have some parameters feeding into it. And so you can now jump straight to, in a couple of clicks, having deep knowledge of the application, and then doing whatever you think you could do from there. And think about this. This is a database session. We could grab a hold of that database session and fire anything we want. We could leverage that on other machines and fire whatever we want to push in there. We could put something out there to cause data to flow up to this, so on and so forth. And it takes a couple of seconds to dig through an application that should be incredibly hardened. Now that's a feature. So what do you think? Do you think you could go up against a hardened application with this stuff? Does it look pretty easy? I mean, that's what I'm going for. Like, even if you're not a hardcore developer, it's like, yeah, okay, I think I could go in and I could do something. And so let's look at that. What can you do? So this attack that I did against that program where we got through the, it was P and then U was the password validation. And so, okay, here's that double equals. Okay, here's the first branch on false. Kick that down, branch on true. And there you go, you throw a not sign before it. And so this is what I'm going for. Like, it's not assembly code, it's not an advanced persistent thread, it's some high schooler with a half hour, an hour of time. And he can just rip apart your program and start firing shit at your server. And of course, we all know the best defense is good sniper. And it's an offensive defensive game. Are you going up against web inspect and you're trying to attack it, it's trying to defend? Are you going up against malware pretending to be AV and it's trying to defend against you? And whatever side you're on, Grey Wolf tips the scales towards the attacker. And then the defenses can build up. And just like we saw with SCADA, the entire point of this is we can't wait 25 years and then say, oh, we should have been defending our applications for the last 25 years. We can start saying, okay, you have protected your web front. Now let's protect your software development front that talks to those same exact servers from the inside, from your terminals. And you can use Packers and crypto, but in the end, it comes down to architecture. So what's the security? We can just bash it across. We can just rip right through most security features. But if you bake in security, that's better. Because eventually they're going to be able to take out your client. They're going to be able to compromise every single one of your security mechanisms. But if you've built a secure architecture, you should be able to handle this. You should be able to have someone malicious on the inside attacking you, and you should be able to withstand that. And let's talk about that. Like, what do we call inside and outside, right? So, we talk about inside and outside threats, but we all know that we can pivot across different points. We can get inside of the internal workings of the enterprise, and then we can take advantage of it from the inside out. So let's do that. Here's one of the demos that I like to push just because I like to encourage security through fear. So say you decompile my application and I don't want you to. Here it is. Here's some ubiquitous application. It doesn't do much, but I want to protect this application. You come in here. This is Reflector. There's ILSpy. There's like 5 decompilers that are pretty solid for .NET at this moment. You come in here, you export it to disk, we'll save it out. And so now we have it saving out to disk. We've accomplished the round tripping, we got your source code, ha ha ha, right? Come in here, go to where it came out to, boot it up, Visual Studios. Oh, I'll need to boot this inside of, oh, maybe it did. This is a offensive payload, so I wanted it. Okay, it's inside of a sandbox, so it won't hit my system. Okay, so we booted it up. Come in here, look at a form. The form doesn't render because the objects in memory haven't been built to render the form. We go through a quick build cycle, and now you can open up this logo and it's just some image. You can come in and you can look at the program source code. However, when you come and look at this about box, and it renders, we get arbitrary code execution, because this is arbitrarily running source code on our system. This arbitrary code execution fires from within Visual Studios as Visual Studios from its memory space on its own threads in a normal standard firing mechanism. Like, this isn't reaching out and running some assembly code or doing something complex that could trip AV doing hooks. It's just straight running source code. And here it is. We have arbitrary source code and we have a small malicious payload running. This, of course, runs in the background silently, either taking developer keys, whatever you want, right? We install this, come in here, and this roots my PowerShell. And here's rooting my PowerShell. Because PowerShell's in .NET, and we can just simply root it with an easy off-the-shelf payload. And it still works. We're just simply rooting the front end. And so that PowerShell is now infected. It could have a keylogger, and it's an application-level keylogger. It's not a system-level keylogger. So it blows right past your AV. And maybe it's an application that has legitimate rights to the internet, so it can just start firing off to the internet legitimately. And we can hopefully defend against this, but when you're an attacker, this is a fairly novel attack vector. And Visual Studios has this in there. How do I do it, right? So let's look at, here's the code. This is the code that fires. This is the logo button, and when this logo button is rendered, its constructor is fired. When the constructor is fired, we see, are you in the process that is this application? No? Okay, then attack the shit out of them. And that's it. That's the code. Put a thread in there, check to see who you're in, and then go malicious. And it's simply here. We add this on the about box, and there it is. And now anyone looking at this form gets attacked. And Microsoft is not going to fix this. This is a feature. This is a known feature since 2004. And so I can push a code project up there, you look at my source code, and now you're infected. You decompile one of my applications, and now you're infected. And so this is why I talk about the going forward 10, 20 years with .NET, we can start defending against these things one at a time and start bringing up vulnerabilities and mitigating them. Because if Microsoft can't run Visual Studios in a secure manner, like, they should have their shit together, right? Like, they push all these documents, okay, if you're gonna run arbitrary code, do it inside of a protected thread with minimal rights and all of this other stuff. But when it comes to actually doing it, no one checks. There is no trust but verify when you come to desktop applications. You simply trust it. You trust it not to divulge your password. And so, let's see what else. How about one more, just for, I haven't got to do this very many times, and I think it's kind of, I've had a lot of questions about, like, how do you like bake in your own attacks inside of your targets. So we'll take this Windows 7 USB DVD creation tool. It creates USB sticks for Windows to install off of. We can then come down, go to our find main, and here's our main. And so at this point we have our application started. These couple of lines are important just because they set some of the context, but after these lines you're pretty much good to go for adding your own payloads. Let's scroll down to these lines in IL, which is set compatibility text rendering. And so here we are. This returns a void onto the stack. So at this point we can put in our own code and the stack is pretty much clean at this point. We'll put in a call. And so I'm trying to make this easy. Here's where we choose who we want to call to. You take your shim that we've been using to inject, you drag and drop it, and there it is. And so now we're linking to an external library. This could easily be a packer that packs us inside of our target. We open it up. We say, okay, fire off void main. That's it. And now we have a void main firing in someone else inside of our target in a couple of clicks. And that's how you develop your own payloads, inject it into them, and then save it out, right? let's save that out. And yeah, run as admin, sure. And here you go. Because we trust this tool. We downloaded it off the internet. It's going to do what we want. We're going to feed it. Okay, sure. Why wouldn't I trust you? And so we close this window. The thread continues because this blocks the thread. It's a thing. But so here we go. We have this ubiquitous payload that we've been running all day long hidden inside of here. Some of the other stuff, just to kind of do some tool dropping knowledge. Go to here. This is, of course, all up on my website for free. I put in a name pipe communication module between all of the payloads, so we can come back to this hack buttons deployer. You can say, let's see, run, I think, right? Send a command to run it, and now we can reopen this inside of our target. And so you can do a sustained communication with it, and it stays live inside of the process. It opens up communication portals. On my website, I rolled it into a Metasploit payload as well. You can then proxy that, do communication over name pipes, over Metasploit, whatever you want, like pretty much anything you want. Let's look at drag and dropping some source code in here, source code viewing in here, and now we can say, okay, show me all of your source code, or change your core variables, or whatever you want. And this is all from that initial 3-4 clicks to put that one call inside of our target. And you can just start going to town like it was your own application. Something else to throw out there that is nice with this is, say you find you want to come to this class, message dialogue, and you see all of these private, private, private. You can come in here, go to access. This is just makes everything public. You come back to this class, and it's public, public, public. And so when you're trying to interface with someone else's API, you can just take control of their API. You can just take control of their program and drive it like it was an API. And when you hook up to someone else's program, just take control. And you can do this to an entire application, DLL, click save, and now it's all public. You can reference it like it's an internal DLL and just drive it like it's a rental. And that's the danger. Like when we talk about Microsoft protecting us, they're not protecting themselves. They're not caring that when they take over our SVNs from a single line of source code, that's a danger. That you can then and there pivot to the rest of the enterprise through the SVN. You can get developer keys, you can get database keys, you can include and bake in malware. And this is a known threat since 2004, and they have no plans on fixing it going forwards. Why not? Because there is no verification from the community. There is no push from the community, hey, I'm getting rooted from this all the time, can you please fix it? So that's partly why I'm here. So when you look inside, you start seeing what you shouldn't see. You start seeing the truth of what's behind there. And that's what I'm bringing you. The ease and knowledge of what you're really running deep in your system. You can find out what kind of login checks they're actually doing, what kind of storage mechanisms they're actually using. When they say they're FIPS compliant, are they just saying that? Like, are they FIPS compliant and like they passed one single test from someone that they paid off, or are they doing good standards all the way around? You can find out what kind of crypto they're using, whether it's home baked or whether it's off the shelf or proprietary and hardened and verified. You can start evaluating what kind of data are they sending home. Like, we just have applications firing home data all the time. What are they actually sending home about you? Do you not want your programs to fire information about you back to the server? Sure, turn it off. Go in there and put a return true at the top of all of the phone home mechanisms, and now you've just taken out the phone home, which is a vulnerability to you. Because if I'm that server, why should I know where your forensics lab is? Why should I know where you are anytime you want to use the program? It's a vulnerability. Someone could use that against you. I could use that against you. You can look at the crypto keys. What are they actually? What kind of vector initialization? What kind of randomization? What kind of standards are they actually using deep inside of their program? And now you can not only verify your programs, other people's programs. You can go to a client and say, program A is secure, program B is insecure because of this technology standard. And we can actually start making informed decisions about our software that we choose to trust. Does anyone have the time on the rest of this talk? Cool. Look at their crypto, see if it's baked in easy, and if there's any questions, I'm more than happy to answer them. And I hope you guys enjoyed this talk and the tools that are free. Well, burning questions or comments, I'm of course happy to take more after, but and before questions and comments, like how many of you do you think you would want to like use this when you get home? Nice. Okay. Good news and bad news game. Good news, my tools are free. Bad news is I slow down what's on the internet by at least 6 months. So everything that you saw from obfuscation to searching and all of that is trickling out slowly. And then good news is I brought a pack of DVDs with some of the newest Grey Wolf on it, and a collection of applications, videos, demos, trainings, everything you need to get off the ground. And so you can pop this in and go straight to town. And of course, free. When I say attack applications, like how many of you want to defend an application with this tech? How many of you would want to verify or attack an application with this tech? I mean, when you think about your competition having your intellectual property with this kind of stuff, like, isn't that a core vulnerability? I mean, when you come to your client, it's like, here's all of your intellectual property, here's an attack against you, and it's all in 15 minutes. Questions, comments? Let's start. Yes? You saw how my program opened the source code?
But do you really see source code to your program?
If you decompile my program, I will sue you. I mean, my program by de facto makes everything .NET open source. So if you can't figure out the source code, you shouldn't use it. My programs are non-commercial. They're not for sale, and you can't buy them, and you can't use them in commercial environments. So that being said, does anyone want to use it in a commercial environment? I mean, just to get a feel? No? Good. See? I did a good thing. I stopped people who would want to from doing it, and all of you, of course, wouldn't want to. And so how about anyone that would actually use it? Like, why would you use it? Do you have any ideas? Yeah. Oh. Yeah.
Firefox.
Sure.
Yeah, I mean, I'll check out this stuff all the time and see how it's kind of about next stage it's actually improving people. I'm going to check. So the first action now that probably
Yeah. And I mean, so it's basically like when you get to check out your desktop applications to find out if it actually needs a password to progress. And there's certain standards, like when you talk about backup software, you do not need a password to see what is in the backed up software. You do need a password to unencrypt it, but you can go through all of your backups and just pull out all of the files that are stored in there and what information was backed up, what dates, what sizes, all of that. And so you can look at community standards. And okay, let me put it this way. If anyone has any really good questions, they definitely get one of these DVDs, which is in a limited supply. So, any questions?
And I take apart Firefox and fix it so I can have an inspector and install the Windows
No.
name and
Not in any way. This specifically and only attacks .NET at this moment, and I don't really have any plans on expanding it out from there. It's a .NET specific only. Sorry. Someday though. Yeah. It's 3.5, 4 compatible. Some of the payloads are 4.2 compatible, and you have to recompile your payload to the target. Yeah. No, I don't.
And
Oh yeah.
if you're not
And when you talk about like good and bad coding practices, like the kind of destruction that you can wreak if just one error is made.
The one use that I've had for this is somebody talking about stuff, and the one use that I've had for this so far is not making extensions, like my line extensions.
Oh. Yeah. And it's a really, so he likes the line-by-line inspections, which when you go to a client engagement, you don't have to say, hey, why don't you send me your entire dev environment and trust me with the keys to your kingdom? You can say, okay, I'm going to go to your website, download your trial, and just get all of your source code. And your clients don't have to trust you more than anyone else. They're just giving out their source code to everyone. And of course, that's one of the first things you get to tell them. Yep. Oh, I'm trying not to attack mono, so no. But I mean, I'm trying to slow down the dissemination of this. So like I said, 10, 20 years, we'll look back and say, oh yeah, .NET's much more secure than it would have been. But yeah, you can, it's pretty easy. Like it's 2 clicks and yeah.
I was curious if you
So when you talk about irregularities between Java and .NET conversions, it's the idea that one thing doesn't map to the other, right? And .NET is a superset of opcodes compared to Java. Microsoft, until version 1.4, developed the Java runtime, and then from there was a little bit of a split. Microsoft went off and did its own thing, and were some of the also public developers of .NET. And .NET has 50 more opcodes than Java. So you can basically implement anything in Java straight in .NET without conversion. To go from Java to, or from .NET to Java, you have to do a little shaking. But no, there's, I've converted massive amounts of Java, and like that IKVM project, I had to convert one line where it set the GUI, and I had to take that out so it didn't use a unique GUI skin. And so it's good to go. Yeah, I attack objects, so sometimes when I'm attacking Java, I have to repoint to a different type of object. But no, it's pretty good. Like you can, and then you can roll it in and use it like it's a core library. And so when we find those Java libraries, and it's like, oh man, if this was in .NET, that'd be so nice. And it's like, no, it is. You just flip it over, it's a DLL, and you include it, and it looks like .NET, it runs like .NET, and you don't have to have the JVM in your deployment cycle. And a lot of companies are starting to use this. When they develop 10 years of a Java application, they suddenly want to go desktop in .NET. It's like, okay, drag and drop. Yeah. I'm trying to encourage Microsoft to want to sandbox the vulnerability in there. And I'm just going to keep putting it out that, like, if someone went up to Codeplex and put in the EULA, I'm going to send your IP and hash back to Twitter when you download and look at this source code, Microsoft might start taking that seriously. And until there is a security reason, there's no financial reason for them to fix it. And that's just unfortunately the paradigm we live in. But no, I'm trying to create social pressure and market and economic culpability. Other questions? Cool. Well, I hope you enjoyed this talk, and enjoy the tools, and thanks. Okay, how many of you asked it? Okay. Okay.